Large language models being developed in a closed manner. So we see a lot of reports and papers talking about them, but often the training data set or the models themselves are not released, and which is, I guess, understandable, but it has many downsides for the research on these kind of technologies. If the training data is not disclosed, then the people that share their code on the internet, the content creators, they don't know if their data is used and they have no way to remove it. This limits the scientific reproducibility of these works, of course, so nobody else can really reproduce that research. And there's also the issue of potential benchmark contamination, which can be very hard to check when the data sets are not released. And then the fact that models are not released also limits the research on various topics on these kind of large language models. For example, on the safety and alignment, or if you would want to study the model's inner workings, or also study some adaptation methods. You can't really do this kind of research if the model weights are not released. And so that's why for BCode we kind of try to be as open and responsible as possible in our research, to try to maybe allow some of the open source community to contribute to that area. And also with the idea that by having more transparent research, maybe it would make these models more trustworthy in the eyes of the users. So yeah, we try to be as transparent as possible by releasing data sets only to train, releasing also the models, model weights, and we try to document as much as possible what we did in datasets cards, model cards, governance, and etc. So that's it for the kind of non-technical aspect of the project. And now I'm going to talk about how we collected the stack. So the stack is a data set of 6.4 terabytes of permissively licensed source code. And we also developed a data inspection tool and opt-out mechanism, and I will come back to that a bit later. So we started with a list of 220 million repository names from GitHub archives, and we just went ahead and git cloned every single one of them. It takes a lot of time, a lot of storage, but eventually you get there, and you end up with more than 100 terabytes of data. And from there, we selected some of the file extensions that usually correspond to actually code, removing, for example, some of the binary files, things like that. And then there's also a step of license filtering. So we worked a bit with lawyers on this step to try to determine what are the file licenses that we could actually use to train and release a data set. And so after this step, we are left with 6.4 terabytes of data, which is the data set that we released. And on top of that, there is a near deduplication step, and we also released the result of that. And so there are these tools that I talked about. So there's a data inspection tool and opt-out mechanism. And the goal was to try to give users more transparency and control as to what's in these data sets, as what's in the stack. And so am I in the stack is basically you can put your GitHub username and it will tell you whether your repositories are actually part of the data set or not. And the opt-out mechanism, the goal is to give people a chance to say if they want their data not to be part of these data sets And so, yeah, if you fill the form, you can remove your repositories from the dataset. So that's it for the data collection, and now I'm going to talk about a bit of the process of training a model on that. And so first about the training data, so of course we use the stack to train our model, but not the whole data set. So and the training data that we use consists of 800 gigabytes of code in 86 different programming languages. There are also GitHub issues, commits, and some notebooks. And yeah, you may wonder, because 2 slides ago I said we had 6 terabytes of data. So how did we end up with this only 800 gigabytes? And the answer is that we did a lot of data curation before training the model. Yeah, this is like, I think, a very important part when you train large language models. And so the first step was near deduplication that I already mentioned. And some early experiments we did showed that this is like a very good idea in general to get better performance out of your model. Then there is a step of language selection. So we only selected, it's still 86 different languages from all the different languages that are present in the stack. We wanted as many people as possible to be using the model, so we tried to be as wide as possible in this language selection. And as I mentioned, we also include GitHub issues, commits, and some notebooks. Then there is a step of data quality inspection. So this is like manual data inspection. So for each of the file extensions in the data set, we inspected around 100 samples. And the goal there was to a bit verify that the different filtering heuristics that we had made sense on each of these different kind of code. And also adjust some of the thresholds that we use to be appropriate and keep only the high quality data as much as possible. After that, we did a step of removing the PII from the data set. So what we did is that so in the first version we were using some regex, and of course removing PII is kind of a hard problem, so it's not perfect, but but yeah, regex can only get you so far. And so what we tried after was we trained an encoder on the stack and collected a data set of PII detection, and then fine-tuned that encoder to actually detect some of the PII in the data set. And finally, there's the data decontamination, and here the goal is just to remove some of the test benchmarks on we will want to evaluate from the data set. So yeah, just to summarize a bit the data pipeline. So after license filtering, the near deduplication removes a bit more than 50% of the data set, and after that, language selection and some of the heuristic filters that result of the manual inspection remove around 70%. And so we're left with 800 gigabytes, which is around 200 billion tokens in our training data set. So now about the model architecture. One of the important choices you make when you train language models is the size and the size of the model and the size of the training data sets on which you want to train. And one of the very useful tools to help you make a decision on that are scaling laws. So you probably heard about that, but scaling laws basically are a set of empirical experiments that try to derive a relationship between the size of your model, the size of your training data set, and your performance, so as your training loss basically. And it actually works pretty well. So you can estimate some of the parameters and actually get a pretty decent estimation of your training loss, just given your training, your model size and training dataset size. And what this does is that if you have a given compute budget, so your compute budget would be roughly proportional to the product of your model size and training dataset size. So if you have a compute budget, so let's say you know that you will have a certain number of GPUs for, let's say, 3 weeks to train your model, then what these scaling laws give you is they tell you what's the optimal combination of like model size and training dataset size that you should use to get the best performance in the end. And so recently, many models are actually don't really follow these laws, and they're often a bit smaller and trained for longer, on larger datasets for longer, on more tokens. And my colleague Harm De Vries wrote a blog post about that, so we like to call it Harm's law. But one way to think about this is that the scaling laws, they take into account your training compute, but not your inference compute. So if you're not going to run inference with your model, then scaling laws really tell you what's the optimal way to trade off between model size and training dataset size. But as you run more and more inference with your model, you're actually better off training smaller models, because your inference costs will become larger compared to your training cost. And so what this graph shows is it starts from a model that's chinchilla optimal, so optimal in the sense of the scaling laws. And as you modify your model size on the x-axis, it tells you what is the compute overhead that you'd have to spend in order to reach the same performance as the chinchilla optimal model. So the blue point, which is the chinchilla optimal model, is the lowest point on the curve. And as you reduce or increase your model size, you get some compute overhead, right? And the interesting thing is that this curve is relatively flat around the blue point, which means that you can really reduce a lot your model size and only get a reasonable increase in compute overhead to get the same performance at the chinchilla optimal model. And so, yeah, so maybe a good spot to be would be kind of in the elbow of that curve, where you have a much reduced model size, so much reduced inference cost, but actually have just a reasonable increase in training cost. So that's one thing to consider when you want to make a decision on what size of model you want to train. And another thing is that the scaling laws, they start from the assumption that you're in the infinite data regime, so that you only see your examples once, at most once, during training. But that's not really our case, because our data set has only 200 billion tokens only. And so there is this interesting work from Hugging Face, where they study what's the impact of not being in the infinite data regime, so being data constrained. And so of course, when you do a lot of epochs on your training data sets, you have a real degradation compared to being in an infinite data regime. But they found out that up to around 5 epochs, you get almost no degradation in your validation loss. And so that's pretty interesting, and that's so we tried to kind of follow these experiments and not go over the 5 epochs marks, because then if you go over that, you start to kind of waste a bit of your training compute. So that's why we decided to train for 1 trillion training tokens. And given the compute that we had, we could train 15B and the 7B models on this training data set. So that's a bit to explain the why and how we decide to train this size of model for this long. And so the model architecture in itself, it's really pretty classic, I'd say. It's a decoder-only transformer. And maybe just the two things that I can mention is that we're using multi-query attention. So compared to multi-head attention here, the key and value projections are shared across all the heads. And the main advantage here is that it reduces a lot your memory footprint and makes the inference much faster than multi-head attention. Then, yeah, other works have used also grouped query attention, which is kind of a middle ground between multi-query and multi-head. The other thing I can say is that we're using flash attention for the attention layer, and this allows, this brings very big memory savings and increased throughput when you use longer sequences. And so thanks to that, we are training with the context of 8,000, which we thought would be probably useful for code applications. And so that's more or less it for the training architecture. So for the training setup, yeah, we trained the model on 500 GPUs. It took around a month. We used tensor parallelism, pipeline parallelism, data parallelism to distribute the training. There are a lot of different frameworks out there for distributed training. Yeah, we chose to go with Megatron. There were a few restarts from the training, but I think we were lucky enough to not have maybe some of the faulty chips kind of silently making your training go in the wrong way. So yeah, we were lucky in that sense. And yeah, so the model, so StarCoder base is the model that was trained on 1 trillion tokens. And so this is a bit to show the different models from that family. And so from StarCoder base, I think many people were excited about Python models, so we fine-tuned it a bit more on Python only. So that's StarCoder. We also trained it a bit more on natural language because we felt it was maybe something that was a bit missing from the training data set. So that's StarCoder Plus, and then there are some of the instruction fine-tuned models, so StarChat. And yeah, we were very happy to see that many people in the open source were also excited about these models and built on top of either the stack or the StarCoder model family, so it was really great to see that. So about evaluation, we've already talked about that a lot these last few days. So the infamous human eval, which is, so it's a set of programming problems, so single function programming problems in Python. And yeah, we argued that it's not a very realistic use case, but however, it's, let's say, a basic that's necessary if you want to have a good model. And so each of the problems consists of a function name and a docstring that gives a natural language description of the problem and some examples of like input outputs of that function. And the goal is to generate the function body. And each of these problems comes with a series of test cases, and so to evaluate the model, we actually execute the code that was generated, and it has to pass all the test cases to be correct. So at the time of release, StarCoder was the best in the realm of open access code models. But since then, so CodeLlama has been released, which is doing better on this task, and also some of the instruction fine-tuned models, so Octocoder, WizardCoder are also doing better on human eval. And so in the paper, so it's not in my slides, but in the paper we do some other evaluations. Maybe one that I can mention is DS1000. It's a set of data science benchmarks, and where you actually have to use some of the different libraries of data science, like NumPy, Pandas, and etc. Which I think is a slightly more realistic use case than human eval. So it's a step in the good direction, let's say. And yeah, so some people have developed a VS Code extension using StarCoder, which is pretty cool. And one thing I can mention is that there is also a membership testing tool in that extension. And so yeah, when you generate some code using the extension, then with a single keystroke you can verify whether the generated code was part of the training data set or not, which I think can be pretty useful. And it's yes, very, very fast to run also, so that's nice. And yeah, we're currently working on a second version because we think in the realm of open access code LLMs, there's still some progress to do. So yeah, it's still a work in progress, so I won't, it's a bit out of scope for today, but just as a teaser. And that's all I had to say. Thank you.
Yeah, thank you very much, Raymond. So we'll go to question and answer session, please.
So thank you. I think it's really, that's really great work. I seem to recall when I read the paper a while ago is that you guys did a lot of work in cleaning the data from vulnerability data, so it's no vulnerable code is integrated, correct? And maybe you could talk a little bit about that? Or if not, like...
So your question was...
so if code is vulnerable, so vulnerable code going into this data set, right?
Yeah.
Yeah. So
that code vulnerabilities, no, we didn't really, that's not, yeah, that wasn't part of the data filtering pipeline.
So maybe do you have any thoughts on that? Is that something important we should be doing, or?
So, yeah, I guess that could be interesting to do. My question is, so I'm not too much from the software engineering world, but what's the proportion of data like repository that has vulnerabilities online? Because I think vulnerabilities are everywhere, right? I mean, there's no code that's perfect. So would we maybe remove too much data if we did that, or?
Yeah, like I guess that's the bigger question. Maybe it's a question for everybody. I guess the concern right now is quantity versus quality, right?
Yeah. Yeah, that's a bit the trade-off, right? Yeah, you have to. But
I don't have an answer, to be honest. But I'm just curious. And maybe if other people have trained these models, what are they doing about vulnerable code if they're removing it? I know that the Meta guys are going to be talking next have done some bit of cleaning on their data, but I'm not sure if the open source models are doing that type of cleaning.
Yeah, we didn't think about this aspect, but yeah, it would be interesting to think about that. Yeah. Thank you.
And you decontaminated the data from the evaluation benchmarks. So I have two questions related to that. One, are the evaluation benchmark also open for public access? Second, is the evaluation benchmark also based on the raw data you collected? You kind of, was this the process that you just pick from that and then remove it from the test set, from the training data?
Yeah, good question. The evaluation benchmarks that we use are all open source benchmarks, and so yes, that means there has to be some repo online that puts some of these examples in their code somewhere. And when we ran the decontamination, there were, depending on the benchmarks, there were more or less matches from the code that we collected. And so, this is definitely something you have to do when you use web crawled data, if you want reliable evaluation.
Hello, thanks for the great presentation and also the great work. So my question, maybe I have missed it, but my question is, did you use any reinforcement learning from human feedback when you built the models? If not, why?
So we do not use reinforcement learning for training the models. So this StarCoder is purely supervised learning using the code we collected. And I think for large language models, reinforcement learning nowadays is mostly used in some of the alignment phase, which comes a bit after. So the RLHF phase, usually. And so that's not something we did there, but it could be done on top of that. Yes, sure. Yeah.
Yeah. So when I read papers, I can see that, for example, for Llama, they would claim that their procedure of reinforcement learning from human feedback really play a very key role in their final performance. So it's not just about alignment; it's also about the final performance. So I'm thinking that whether that's necessary in the scenario of code generation and other software engineering tasks.
Yeah, I guess there could be some performance gains, but for example, also one of the when we evaluated the models, and for example in human eval, one of the main failure cases was that the model, instead of generating a solution, generates a comment. For example, to do, the solution goes here, and goes on to the next function. So. And this is an alignment problem because the model doesn't do what we want it to do, right? So I guess from aligning your model, you also get better performance. Yeah, right.
Thank you.
Thank you for the great talk. I actually have a question similar to the first question. It's about the data cleaning. I'm wondering if you have used some strategy to identify or to filtering out the code data of low quality, like filtering out the code from the GitHub repository of low stars or low forks, or just delete the files which less than 3 lines of code, or just delete the code that start with comment like automated generated, something like that. Because these are some small tricks. When I talk with some industrial guys, they are trying to building some models, they will try to make up some strategy to try to filter out some poor quality data. So in summary, my question is that, is there any definition for the good code quality in terms of training a code model compared to the traditional code quality regarding to the traditional software engineering, like a bug, something like that? Thank you.
Yeah, good question. So data curation is really a very important part, and so yes, I mean, it's exactly as you said, like it's a bunch of heuristics, of tricks, to try to filter out the low quality data. And so basically, I mentioned that we looked at some samples for the different file extensions, and basically what we try to focus on is, so we want to keep everything that looks like code, so we didn't really look into like the quality of the code, whether it's it is good quality code. We just want to remove some of the there are things that are just, data inside some of the files, and so we don't want to train out that. There are, sometimes you have random sequences of character, you have binary files, and so the goal was mostly to remove these kind of things, and it goes through, things like, checking the average length of the lines, the maximum length, the percentage of alphanumeric characters, and some heuristics to remove the automatically generated files. It's really about heuristics and manual inspection.
Yeah, maybe one last question.
So, will there be a StarCoder 2? What's next for that?
Yes, there will be a StarCoder 2. It's a work in progress, and we're working on that, and it will be coming soon, I hope.